Section 11.2, Goodness of Fit. Previously, when we studied probability, we always assumed that a die was fair. Every number was going to come up about the same number of times. Well, is it possible that a die is not fair? How would we check? This is where we can use the chi-square statistic to figure it out. Let's say we were to roll a fair die 100 times. And actually, let's make this 102. It'll just make our math work out a lot better. So let's say we're going to roll a fair die 102 times. We would expect each number to occur with a probability of 1/6. So there's 6 possible outcomes. Each one is equally likely, so 1/6. In other words, out of 102 rolls, each number should come up about, or actually exactly, 17 times. So that 17 comes from 102 divided by 6. Well, let's say we're going to play a game, whether for fun or for money, however you decide to do that, and we're not too sure about this guy. So we get our hands on his die and we conduct an experiment and we roll it 102 times. So I'm going to alter our data here just a little bit, probably not very scientific, but believe me, this will make our numbers work out a lot nicer and we won't have to deal with any fractions. Okay, so we roll his die 102 times and we get the following results. The number 1 comes up 18 times. The number 2 comes up 19 times. The number 3 only comes up 8 times. That seems a little unusual. The 4 comes up 14 times and the 5 comes up 25 times. That seems a little unusual as well. And the 6 comes up 108 or 18 times for a total of 102. Now we can't make a conclusion just based on the numbers. We can't say, oh well, look at the 3 and the 5. That's not right. We don't know if that just happened by chance or is the die really not fair or loaded. So that's where we test with chi-squared. Well, before we work any numbers, do any calculations, we need to set up our hypothesis. For a chi-square goodness of fit test, the null hypothesis should always say something about there being no difference or no change from what's usually expected. So on the die, we usually expect each number to come up an equal amount of time, so I'm going to say it something to that effect. Now you don't have to be very exact here, meaning there's not a prescribed formula the way we used previously when we had things like mu is greater than a certain number. This is just kind of plain English here. So I would say maybe for the null hypothesis, each number is equally likely to occur. Meaning the die is fair. So the alternative would be that each number is not equally likely to occur. So the die is not fair. So the main thing you want to keep in mind here is the null hypothesis is pretty much saying this is how it usually is, and I think it's still that way. But the alternative is saying, no, something's different, something's changed, and we're trying to prove or disprove that. Okay, now we have our hypothesis set up. Now we need a test value or a test statistic, and that's where chi-squared comes in. So chi-squared looks like an X. It's a Greek letter X, and the formula for chi-squared is this summation here, O minus E quantity squared divided by E. So O is the observed frequency. So that's the numbers you got from actually conducting an experiment. E are the expected values, what you expect to happen based on how things usually go. So for us, we usually expect each number on the die to come up roughly the same amount of times. So we're going to take the difference between those two, square it, and then divide by the expected value again. And with degrees of, for chi-square, kind of similar to our t-table, we're also going to need degrees of freedom, and that's the number of categories minus 1. So you can think of this as n minus 1. But let's get that test statistic calculated first. I'm going to use a chart here, kind of doing it by hand. You are certainly encouraged to use your calculator to speed up these calculations, Or for those of you who either don't have access to that calculator or don't want to use it, kind of show you the long way, and maybe you can get an idea of how you would do it. You would prefer to do it later. So here are my observed values, which come from up here. Let's see, 18, 19, 8, 25, I believe was next. And then 14, oh, nope, I skipped something, 8, 14, 25, and 18. Okay, so that's what happened when I actually rolled the die. For expected, since we rolled it 102 times and there are 6 possible outcomes, we expect each outcome to come up 17 times. Then I want to take the difference between the observed and the expected. So that'd be 1, 2, -9, -3, 8, and 1. And probably if we added those up right now as they are, we get something very close to 0, which is why then in our formula we are going to square each number. So 1, 4, 81, 9, 64, and 1. And then finally take that number and divide by the expected value. 0.0588, 0.2353, I'm rounding to the 4th decimal place, 4.7647, 0.5294, 3.7647, and 0.0588. And our final step is to add all of those up. I get 9.4118 if I round. So I didn't necessarily round the numbers here on my screen. I used my calculator, so I have a few more significant digits there. Okay, that's our test statistic. Well, remember with previous hypothesis testing methods, we had to compare our test value or our test statistic to a critical value. And this is where we're going to use our chi-square table. And we're doing 10% level of significance. Now, chi-square table is kind of set up like a t-table where we need the degrees of freedom. And our degrees of freedom here, remember, are the number of categories less 1. Well, there's 6 possible outcomes on the die, so -1 is degrees of freedom 5. Now, what is different about a chi-square compared to a t is this is a skewed distribution. T-square, or student's t rather, was symmetric the way normal distribution was symmetric. The chi-squared is skewed, so it has this tail going off to the right. And what we're looking for is what this value is here. The 10% level of significance is telling us, is telling us that this area is 10% or 0.1. So on our table, we first have to go down and find our degrees of freedom. And let me explain real fast about how this table works. Over here you have these values 0.995, 0.99, 0.975. And this is the left side or left tail. Now I hesitate to use tail because on the left side there's really not a tail. You have a big hump there on the left side. So if we were finding something on the left side, we'd use those values. For hypothesis testing in this regard, we'll mostly be using the right side or right tail, which does look traditionally more like a tail. So notice how small these values are, 0.1, 0.05, 0.025. So first I go and find my degrees of freedom, which was 5, and I go over to my significance level, which is 0.10, and here's my critical value right there, 9.236. So what that's telling me is back here to capture 10% in the tail, my chi-squared value has to be 9.236. Okay, now just like we've done in a lot of other tests before, I need to compare my test value that I obtained from doing the observed minus the expected, squared, all that, compared to this critical value. Well, we got previously 9.4118, which barely, it just barely falls in that area, that rejection region. So we would say we reject the null. Hypothesis in favor of the alternative. And remember to always put your conclusion in the context of the problem. We could say reject or fail to reject all day long, but if you don't tell me what that means in the context of the problem, then you haven't really given useful information. So rejecting the null here means that there is evidence to suggest that each number is not equally likely to occur. So I guess short and sweet we would say the die is not fair. Now it would be up to you as a person doing the statistics if you wanted to either conduct another experiment or roll the die more times, because if you notice our test value is very, very close to that critical value. It is possible that in another roll of 102, or another experiment rather, of 102 rolls of the die, we could be on the other side of that line. So sometimes when you're that close, you might want to reinvestigate just to make sure your conclusion is sound. But for the information that we were given in the observed values and calculating the expected values, this conclusion is correct.